Okay? Just in time for John to open the can. Good afternoon, everybody. Welcome to another edition of the Kent Seminar Series. I am normally fairly outspoken about my desire to get outside speakers in here and try to diversify as much as possible. But today I think is a bit of a rare exception to that, because we do have one of your colleagues speaking today, Jeff LaHucik. Yet I think he's going to be telling us quite a bit about a topic that most of us don't know too much about. So I think it'll be extremely informative for everybody in this room. And Jeff is here several days a week working on this project, yet many of you probably didn't even realize that. So again, please join me in welcoming Jeff LaHucik, and he's going to tell us about roller compacted concrete.
So I'll be talking about effective aggregate packing structure on RCC. First of all, a little bit of introduction of what is RCC for those that aren't familiar with it. It's a no-slump concrete, so it's basically has no workability. And when you compare it to a typical Portland cement concrete, it has less cement, less water, and more aggregates. The less cement and water is what contributes to its lower workability. And as you can see, it basically looks like damp aggregates, just enough cement and water to coat the aggregates and not much else. And then how is it constructed? Basically the same as asphalt. It's brought from the mixed plant in dump trucks or even just typical concrete trucks and placed into a paver, and then the paver can either just be a typical asphalt paver, or if the contractor is experienced with RCC, they probably have a modified high-density paver with a screed bar at the end that will get densities of like 94 or 95% coming right out the back. And then afterwards, it's compacted with rollers. Typically, a vibratory roller goes over it first. That's seen in the bottom right. And then a finish roller, just a smooth static steel roller, will come behind it just to give the surface a nice finish. And density is the controlling factor. It's typically 98% of the modified proctor as measured by like a nuke density gauge. So why use RCC? It's cheaper than typical concrete and potentially asphalt as well. Uses less cement, the most expensive ingredient. Faster construction, you can get more yardage for a given day. And then you don't use any reinforcements, so you're saving on all that steel cost. And you can also reduce your saw cutting by using longer joint spacings. Some of the drawbacks are its moisture sensitivity. Since you're designing it based on a maximum density from the proctor test, any deviation from the optimum moisture will either cause the mix to segregate or it won't be able to be compacted to a certain level. The mix design is similar to asphalt. It's pretty involved compared to concrete, where it's a simple step-by-step procedure. First, you have to choose your aggregate structure, then you also have to do the proctor test, and then depending on whether or not that worked or not, redo it. There's also big discrepancies between field cores and companion cylinders. One of the thought processes behind that is that there are different compaction types. Companion cylinders are made with an impact hammer, whereas it's compacted in the field with a paver and rollers. It's a rough surface, as you can see in the right, so it's typically only used on low-speed roads or parking lots, and it's typically about a 45-minute window from when mixing starts to when you can compact it. Otherwise, we get this. It's deterioration and spalling at the joint, as well as cracking after, I think this was 2 days after placement. So to get into the study, the reasoning behind this is to look at whether or not typical concrete aggregates that a ready mix supplier has on site can be used to make good quality RCC. That is basically that it's low fines, while PCA and ACI and such agencies, they recommend higher fines contents compared to typical concrete aggregates. So we're going to look at moisture density relationship and mechanical properties of RCC to see how gradation has an effect on those. So we fixed the cement content at about 475 pounds per cubic yard, a little bit less than IDOT's minimum, which is, I think, 520. And this is shown to give us good results, and we thought 520 was a little overshooting it. So then for the gradations, kind of the two key factors that we want to look at were coarse to fine aggregate ratios. As we saw in that mixture in the volume, as we saw here, there's a lot higher aggregate content and specifically fine aggregates, so we wanted to take a look at the relationship between those. And also the deviation from the maximum density curve. Typically RCC is recommended to just make the gradation as close to the max density curve and you should be fine. And we set the nominal max size at 3/4 inch, which is recommended to get a good surface finish. Just so some of the aggregate properties. We used 4 aggregates in this study, just coarse dolomite that we have in the lab and dolomite chips, as well as a natural sand and some mineral filler for the higher fines mixes. So we did 9 mixes that had low fines and 3 mixes with increasing fines contents to test the effect of the gradation for the first 9 mixes, and then for the last 3 to see how increasing fines contents affects the RCC. And this red one here is the max density curve going all the way up. And that's kind of repeating it. But so mix 10 has 3% fines, 11 6%, and 12 of 8.24%, which is what the max density curve recommends. So then designing the mixes, you do a modified Proctor test. Anywhere from 5 points gave relatively good curves, and some had to use 7 points to get a good fit. And from that, you use the maximum dry density for quality control in the field. That's how they would specify the minimum density. And your optimum moisture content is what you aim to batch the concrete at. And we've seen that it's quite susceptible to the optimum moisture content. And if you're too wet, the mix will segregate under the roller and won't support it. And if you're too dry, you won't be able to achieve density. So to look at the effect of the density and moisture on strength, I poured 2x4s out of Proctor samples and plotted here. That red line corresponds to 98% of the density, and the strength decreases about 1,500 psi from the maximum just by decreasing density by 2%. So it kind of validates the minimum 98% that is typically specified in construction, and shows that the large effect of moisture on the hardened properties. So then creating cylinders in the lab, you use an impact hammer. What's on there is, on the tamping rod, is currently a 3.5 inch diameter tamping plate to make 4x8s, as well as the circular one on the bottom is about 5.5 inches to make 6x12s. And then currently the ASTM spec only specifies 6x12 inches, but we're also looking at 4x8s. I'll show some results on that. So and then we had a control mix that was just a typical plain Portland cement paving mix to see how RCC compared with it. And all of the RCC values except one were greater than the control, the average values, but mixes 4, 5, 7, and 8 were statistically greater than the control, while all of them met or just barely met IDOT's minimum 28 days of 4,500 psi. And these were tested at 14 days, so they're far exceeding the minimum strength requirements. Splitting tensile, the variability for this test is quite large. One thought is that we're compacting in the vertical direction, and we're unsure of the horizontal compaction that's occurring, so splitting it on its side is going against the direction of compaction, and that's one thought process. But they all compared similar or greater than the control mix. So, and then we've also done some fracture testing with Armin's help of teaching me. So we one of the benefits of using the DCT test as compared to typical the SENB test that's for concrete is that there's only an ASTM spec for making 6x12s, which is what you would cut DCT specimens out of, so that works well. Otherwise, you'd have to make SENB beams, which has been done by Alex, and Eric did that. There's no spec for making those beams. So to test this, to test using the DCT, we measure the load versus crack mouth opening and load it, and once it reaches its peak load, we unload it to get the unloading compliance and then reload it again until failure or around 0.1 kilonewtons. Just for reference, some of the equations that are used to calculate fracture properties. The main ones that I'll be talking about are the K1C, which is kind of a materials resistance to fracture or crack propagation, as well as the total fracture energy, which is energy required to propagate that crack. So these are looking at the fracture results in terms of total fracture energy. This is typical variabilities for DCT testing, and we can't statistically conclude that RCC is better than a typical mix, but all the average values are greater, and can have some confidence in making that decision. And this is where RCC really shows its improvement over typical concrete, is the K1C, or the critical stress intensity factor. It's thought that the denser aggregate structure of RCC is interfering with that crack and making it the crack pack more tortuous, and also halting cracks and preventing their propagation. So this control is typical of early age concrete fracture, about 0.9 or 1 or slightly over 1, whereas RCC showed 1.2, 1.4, around that range. So then, using the gradation properties and using the Bailey method, the FAC ratio from the Bailey method, the coarse to fine aggregate ratio, which is one of the things we wanted to look at, as well as percent retained on 1/2 inch and number 8. A regression was developed for the low fines mixes in the blue there. Found good agreement. There's a caveat that it's only for a certain cement content and just for those aggregates that were used. And then when comparing that to these higher fines contents, there's basically no agreement. That's an area for future research, is to see why these fines contents were, so different. And one of the interesting things that we saw was that 3% fines gave it significantly lower strength than any other mix. And 6% being greater than the 8%, which according to the max density curve is what should be the optimal. It's kind of expected because the gradation doesn't take into effect the cement, and using less fines than the maximum density curve says, and then adding in cement brings you close to it, whereas if we use optimal fines and then add cement onto it, we're actually dispersing the coarse aggregates. So that would be an interesting trend to see if it keeps going forward with different coarse aggregate structures. And then comparing the 4x8s versus 6x12s, they don't give one-to-one results, but they can be correlated well. You wanted to do this first to use less material. It's a lot less sieving to do, a lot less material cost and whatnot. Also, it's interesting for testing agencies. It takes up a lot less room for them, and it's easier for them to transport. So we're happy with this, and some of the other mixes that have been done where the gradation wasn't controlled, this relationship doesn't exist. It's possible that it's due to segregation, or it could be larger aggregate sizes that are affecting the relationship between the two. That's something else to look at. But we can relate the two, and with more testing, it could be brought up to ASTM to possibly include the 4x8s. So some of the conclusions that we can make are that we can use available concrete aggregates even though they have much lower fines contents that are typically recommended. And it can achieve similar strengths to typical concrete, compressive and splitting tensile, but it is recommended that we either use a larger sample size or a greater factor of safety when designing due to RCC's tendency to have higher variation. And for content cement and for the aggregates used, we can predict the compressive strength just from the gradation parameters. And also, fracture properties are better for RCC than typical concrete due to the higher aggregate content and denser packing. Some of the things we want to look at further as to the effects of aggregate structure on RCC are strength and fracture optimal along the max density line, or is there an optimal gradation that yields the highest properties, and how do fines contents affect this, and should we include cement in the gradation as well and optimize the gradation while including cement. And future research for RCC in general is we want to look at using the superpave gyratory compactor, and the thought behind that is to correlate better with field cores and companion cylinders. The gyratory compactor with its shearing action will more closely resemble the in-field compaction. Also want to look at fibers, their effect on RCC, since steel reinforcement isn't used, can't be used in RCC. We want to see how fibers will affect the toughness of RCC, as well as can they be used to increase the effectiveness of joints or even extend them. And we want to look at using recycled materials like RAP or RCA or steel slag in RCC. Since RCC has a lot more aggregate in it, we can get rid of more of those recycled materials by placing them in RCC. And I'd like to thank ICT and IDOT for funding this project.
Question for Jeff.
Yeah.
On the first slide where you talked about the proportions, I wanted to ask you what the difference in freeze-thaw characteristics of roller compacted are versus conventional PCC, since the air contents are significantly different.
That's another thing we are also looking at is, especially with the low fines, is we're not compacting, or the voids. First, we get air voids that are typical of concrete, and also having compaction voids, whereas we're not filling the structure as much as we expect. It's shown, there's been research on freeze-thaw of RCC, and it's all failed in the lab, but there have been field studies where they're using it in Canada, and it's been there for 20, 30 years and holding up fine. One of the difficulties is there's no standard for molding RCC in typical geometry, So people have found that there's trying different geometries, and it's difficult to measure the dynamic modulus. But there hasn't been a lab study that shows that RCC passes, but in the field it's shown to work. So there's a big discrepancy there.
What were the differences between the different RCC mixes that you used in your study, basically? So I see control, and then I see like 1 through 10.
Oh, control is just a typical concrete mix. It's not RCC.
Right.
We just wanted to see how it would, how RCC compares in relation to a typical concrete. So if it's worse, then there's no reason to use it. But if it's better and cheaper, then why not?
But I mean, so are these different mixes? Like 1, 2, 3, 4, 5?
Yeah. So
How
1
do
through
you-
12, the only difference between them is their gradation. They have the same cement content. They have relatively the same optimum moisture. For all 12 mixes tested, it ranged from like 6 to 7.1. So it was a very narrow range of optimum moisture, but it was the same aggregate materials. So
Could you go back to the, sorry, to the, I think, stress intensity plot? Okay, and then you didn't show fracture energy in this presentation, did you?
total fraction energy,
Okay.
yes.
Okay. Okay, and then you probably ran stats analysis on these results.
Yeah, this
Did you
is.
find that they were statistically different or like significant or?
They were. I mean, the COVs for total fraction energy are around like 10, 12%. So we can't really statistically conclude that there's a difference between the control or typical Portland cement concrete and RCC, at least for total fracture energy. But from the average values, they're higher.
Thanks.
Mm-hmm.
You took away my initial question by mentioning that you were planning on investigating the effects of gyratory compactor. So I guess my second question would be, because in a room like this, when you have a bunch of pavement engineers, it tends to be black versus white or PCC versus HMA. And you've shown that this has the potential to actually perform at least as well as conventional PCC, possibly even outperform. And you briefly mentioned the cost. Do you have any idea how the cost of this material does compare to the conventional PCC or even HMA?
It's for concrete, I think it's about 70 to 80% of typical PCC. Asphalt, I'm not sure, depending on oil prices and whatnot. And it's typically used as a composite pavement due to its poor surface finishability. So all the studies that I've seen, it's typically anywhere from 6 to 10 inches of RCC with a 2-inch asphalt surface course.
Does that cost include labor and equipment?
Just total cost, yeah.
Okay.
You say overall that it's very sensitive to the moisture content. With that in mind, all of your mixes use dolomite. Would other aggregate sources, change this considerably, or is it's all based on your Proctor optimal moisture?
Change the sensitivity.
Right, strength values.
I haven't seen anything in the literature about how aggregate types affect moisture sensitivity, but in general, it is pretty sensitive. There's an optimum, and it falls away pretty fast on either side.
Along those lines, when you make these designs, conventional concrete is by the SSD method or surface saturated dry. Is that the same method here?
RCC is based on the oven dry weights.
So absorption would matter. That's what I was wondering. What about, you talked about density testing with a nuclear density gauge. Is there a lot of variability in that with the backscatter mode? Do they use a mineral filler like for HMA?
When I was on a site when they were paving at an oasis, they did it in direct transmission, so they just hammered it down into there. I don't know about the variability of it, but they do it in direct transmission.
What did they
do with the hole?
They left it. But it was being covered, so
Oh, they're putting asphalt?
it was being surface treated. So.
You early on talked about the production rate of this material being better than HMA. Aaron asked about the cost. Is there any quantification between how many lane miles a day you could do versus HMA?
I'm not sure of that. My guess is more because you can do up to, depending on the agency, you can do between 8 and 10 inches per lift. So you could potentially just go one lift all the way down.
Do you do a single lift when you compact in the mold, or do you treat it more like
No,
a rocker of unbound material?
The 6x12 is done in 4 layers and a 5th time just to finish the surface. For the 4x8s, I did 2 layers and a 3rd time to finish the surface.
Actually, to expand on Greg's last question, do you have any idea what the cure time is required before open to traffic, even if it's construction traffic for an overlay, for example?
Cure time, it's basically just based on strength. From what I've seen, as long as they can achieve their strength, I think they'll open it at 1,500 or 2,000 psi, and then they'll completely open it to traffic after it reaches, I think, 4,000 or 4,500. Yeah, curing is a little bit less than typical concrete.
Any other questions?
Have you done any coring testing or strength test versus your compacted molds and see what tensile strength is there versus your molded?
I was hoping to, but
Oh, okay.
didn't get to it. I got too cold too fast.
Stay tuned.
Yes.
I forgot my question. I don't care.
Okay, thank you, Jeff.